Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series called Insular Industries. Here, we will highlight just a few of the cultural blind spots that some mega industries have in certain web handling areas. In this show, we will cover another of the oldest, largest, and most proficient of the web industries, metals. If they can have web handling blind spots, pretty much anyone can. I know your time is precious, so let's get started. Metal has been rolled into strips and wound into coils for about a century. A little longer for steel, a little less for aluminum. Metals is one of the largest of the web industries and is valued at about $200 billion per year annually, or just a little less than paper. These mills are impressive in their size. Some plant complexes have more than 100 acres under roof. These mills are also impressive in their energy consumption, both for heating the metal and the motors required to turn the rolling mills and winders. Finally, these mills can produce sheet with tighter thickness tolerances than many other webs. Even so, as we will see, metals have cultural blind spots as big as the mills themselves. Specifically, we will detail two examples here, guiding and splices. One example of a cultural blind spot you may occasionally see in the metals industry is strip guiding. As a point of reference, most web industries can hold web position to better than a few hairs thicknesses. They use theoretically sound and field-tested geometries, such as given in this list. We need not detail how to do that because path control and guides is covered in chapter-length detail in the must-have 750-page Web Handling Handbook. It is also covered in my award-winning and trademark Web201 class that has been taken by 5,000 students. In any case, occasionally the metals industry fails to hold path position within a few inches. This can cause crashes and strip breaks and the associated waste and delay of these events. In all the cases I've thus far seen, it was simply because the machine builder did not follow the half-century-old rules for guide design. In review, there are two major considerations for effective guides: wrap angle and span length. The wrap angle on the guide roll should be close to 90 degrees. The span length depends on a number of factors detailed elsewhere, but mostly upon which type of guide is being used. The steering guide requires much longer paths than the displacement guide. The reason, my students will recall, is the severity differences between in-plane bending and out-of-plane twisting roller misalignment. Now, let us examine two strip guides that I was called upon to troubleshoot. The causes for the abysmal performance was simple. They broke the long-known design guidelines as shown in these two figures. First, the wrap angle in neither one was not 90 degrees. In the top figure, the outgoing span is at great risk for buckling and web breaks. On the bottom figure, the incoming span would be troubled by diagonal wrinkles. In both cases, there were other design rules that were also broken. In both cases, the guides were as close to inoperable as is possible to operate. Perhaps the good news about this is the contrast with the paper industry. While almost all felts and wire guides in the paper industry are improperly designed, most strip guides in the metals industry do follow the rules. Still, if you are one of those unlucky few whose builders did not go to school, you will appreciate the concern. Splices are a weak spot and a trouble spot for almost all industries, and metals is no exception. Web breaks are one possible trouble. Path control due to crooked splices is another possible trouble. However, metals adds yet another trouble that is entirely avoidable. Standard practice is to punch 3 large holes, gigantic holes, in the strip to serve as splice markers that can be detected with a simple photo eye. You can see some big insecurity in having 3 large holes in splice detectors when there are many other options that may even be more reliable, particularly if you factor in the problems we will discuss now. First, the holes create MD stress concentrations, which can halve the strength of the material and quadruple the web break rate. Second, the holes create CD compressive stresses and thus risk MD wrinkles. Third, the holes are placed in close proximity to the stitch. That is to decrease the splice weight. But in the process, it increases the web break waste rate. I could think of a dozen other alternatives to using holes to marking splices, but a single voice will not likely budge the metals industry out of their decades-old blind spot. I do not work in metals as much as other industries, so, as a consequence, my list of other blind spots is not quite as large. Still, I have observed a common tendency to oversize roller diameters. How to size a roll is well detailed in my 25-year-old roller book that is still in publication, as well as a chapter in the must-have Web Handling Handbook. Another common trouble is tail cutting and transferring to the next coil. Often, the tail of the strip is expected to travel straight for a dozen feet between the cutter and the core. Of course, it won't travel straight. And of course, the resulting offset just above the core may be large enough that the entire coil might need to be scrapped. Finally, while most metals are wound on a strong steel core mandrel, occasionally it is wound on a flimsy cardboard fiber core. No surprise that the core may crush. Thank you so very much for joining me in this Insular Industries mini-series. Please join me next week where we will continue our discussion of cultural handicaps by critiquing the oldest web industry, textiles. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.